Come in.
No.
No? Oh, they're totally lost. Okay. Now. Okay. Where's it gone? First question here. Number 6. There we go. Okay. Now we haven't really done it so much in class. So before I do this question, I'll talk a little bit about this. But a while ago we said Young's modulus. Were you in this class, Adil? I think you were. Young's modulus is stress over strain. And actually there's a formula for stress and strain. The stress is a lot like the pressure. It's the force over the area. And the strain is the change in the length divided by the original length. So this thing here is called Young's modulus, stress over strain. And this is the definition of stress and strain. So if we were to draw a graph of this, let's put it here. So on this axis, I'd like to put, what did they ask for? Force against extension. Force against extension, delta L. So you know that this is a constant. It's called Young's modulus, it's a constant. And it equals stress over strain. So if I just rewrite this a little bit, I can get Young's modulus times delta L over L equals stress, which is F over A.
So which page are you on?
It would be page 23. So I get F equals YA over L, if I bring the A up here, times delta L. Sorry, that's an A there. So what happens as I increase the extension? What happens to the force? Does that mean I have more force or less force? Must be more. And if there is no extension, then there's no force. Sorry if you can't see there, I'll write it again. That is Y delta L on the top there. Y A over, that's an A, over L. So no extension means no force, and then as I increase the extension, I get more force. And that's normal for most materials, okay? So I don't have anything, like here, with this strap on the bag here, okay? As I pull this one here, the delta L gets a little bit bigger, and then the force gets bigger as well. But what happens if I keep pulling it? Well, if I pull it enough, it won't actually snap back into place anymore. It's a bit, I don't know if you've seen it before, but it's like when you have a spring, and if you pull the spring too much, and then it deforms, and you let go, it doesn't snap back. So in fact, if you extend something too much, you break it, and you get no more like force that can snap it back. It loses its stretchiness. Do you get what I'm saying? So for the graph here, this part of the graph is called the elastic part. But then if you extend it too much, it breaks, and then it's no longer, it kind of flattens out then. It no longer can have any more force. So that point there where it changes is called the elastic limit. And then if you extend it past that, you break its properties. It can no longer be like a spring. So like I said, we didn't really spend any time on Young's modulus, but there is not much to say about it except what the formula is and this graph. Okay? Scroll up. Yeah. Okay, so that's A part 1. Oh good, I have A part 2 done. show where the elastic limit is, that's there, and what's called the deformation. The deformation is the part where it breaks, so that's the name of this part here. Now I don't know if you know this word from English. Deformation or deform? What does deform mean?
Like split it.
No.
Like split or like...
Like it's changed.
Yeah, can we give an example? Like how would you use this in a sentence in English?
I deformed Play-Doh.
Yeah, but...
It's not in the correct.
Make it a bit more unique, because you can do many things with Play-Doh.
I'll tell you one.
Yes?
Brandon is deformed.
So can I say?
Brandon, do you want to know something? Do you want to know something? I was thinking about making that joke, but I thought, no, I have to draw a line. That's too harsh.
That's exactly what I was going to say. That's a deformed baby.
Yes.
That just go too far. I didn't want to say.
All right. So we're all clear.
Yeah, we know.
I don't know.
You understand?
Deform. It's a word in English, and it means something looks really broken and ugly. So she used Brendan as an example. So we say that piece there is deformed because that's the broken part. Okay. Or the Brendan part, if you will. Sorry, see, I wasn't going to say anything, but then she opened up the gates and I'm like, oh.
I'm 19 years old. I shouldn't be experiencing this anymore.
Oh, you
It's so sad.
you can handle it, Brendan.
It's okay, he was the boy that sat in school a milk
No
bottle.
matter. That was the first year, okay? And then like next year I owned the school.
Oh, yeah.
Then you turned into a beautiful butterfly, yes. Yeah. The story always has a happy ending. Alright, so that's A part done. Now, the B part. So, again, this is, if you look at the B part here, it's a lot, are you writing down there? If you look at the B part, it's a lot like a section A question, okay? They give you the length, so you have a piece of wire, and you got the length here, and you're told its length is 1.5 meters. And you're also told the diameter is 0.8 millimeters, which means the radius is 0.4 millimeters. And you're also told that the Young's modulus, I'll just write y, equals 1 times 10 to the 11, so it just equals 10 to the 11. And maybe I should draw this upside down, because what they're saying is that this wire is being hung from the ceiling. So if it's being hung from the ceiling, there's a force pulling it down. They said there's some 5 kilogram weight hanging down from this wire. So what would be the force here?
5G.
It'd be 5 times G. 5G. Because that's the weight pulling it down. So we have the F, we have the Young's modulus, we have the length, we have the radius, we have the diameter, and we are asked for the stress. So we have 2 formulas with stress in it. Young's modulus equals stress over strain, and then the other formula we have for stress is force over area. So which one do you think you would need to use here?
Force over area.
Yeah, force over area. So can you type this in on your calculator, please? 5G over pi or squared. That's 10 to the minus 3 because of millimeters.
Wait. 97.58 times 10 to the 6. Because
10 to the 6, yeah?
Like
We trust you.
Ali was like,
Yeah.
oh.
Yep. Yep. Okay. That's stress. Now, we want the stretched length. So in other words, we want the extension, the delta L. Okay, so we have formula for strain. strain equals L over, delta L over L. So therefore, what does delta L equal? That would equal the L original length multiply the strain. Now we know the original length. Could we know the strain? The answer is yes, because we know Young's modulus. We've just worked out the stress, so we can get the strain from this here. So can you type in, please, strain equals stress over Young's modulus. So 97.6 times 10 to the 6 over, now what was Young's modulus for this question? 10 to the 11. Oh, well, I can see what that is. That's just going to be 10 to the minus 5 up here.
Minus 4. Oh, no, yeah, minus 5.
Yes.
Near 9 points.
Yes, yes. Yeah, if I kept it like that. So delta L equals 1.5 multiplied 97.6 multiplied 10 to the minus 5. And what's that, please? And they said they want the answer to 4 significant figures.
1.4637, so 1.464.
Yeah.
Times 10 to the minus 3.
Oh, good. So that's 1.464 millimeters. Good. Okay. And that is B done. So now on to part C in a moment. You got that? Okay. Can I scroll down?
No.
Oh. When there's something that maybe can just pop under this just to... No, that's okay.
It's hot.
There. Yeah, can you open the other window? I have a noob. Go.
You should open it with one hand. You go to the gym.
Oh, that's true, actually. How long until you can open it with one hand?
It's a window, isn't it?
Your manhood's in question.
Hey, Brandon, how often do you go to the gym?
Oh, never, no. But I have to.
You're comfortable with this, yeah. All right, part C now. So, first part is state Boyle's law. What's Boyle's law? Do you do this one in chemistry as well? Boyle's law.
Vol 1 P1 equals Vol 2.
What is it?
Vol 1 P1 equals Vol 2 P2. Or Vol 1 P.
No,
Vol
give it to
P.
me. Give it to me as a proportional.
All right. Vol 1 over P1 equals.
Nah, that's not what I'm looking for. Say again.
Right. What do you mean? Vol times P equals.
Okay, I know what you're giving it to me. You're saying P1 V1 equals
P2
P2. But I like to say P is proportional to 1 over V. Well, okay, that's fine. No, both is acceptable. But in both cases, the key thing is at constant temperature. Okay. A gas cylinder has volume 2 times 10 to the minus 3. It contains 1.5 moles and the temperature is 300. So I want the pressure. Well, what do you have to do here to get the pressure?
We have to use the
Ideal gas law.
law.
PV equals nRT. So P would equal nRT over V. So that's 1.5 times 8.31 times 300 over 2 times 10 to the minus 3. So what do we get there for pressure, please?
I think there's 18697 50.
50.
1.87 times 10 to 6.
Yeah, like this about. Pascals. Okay. Now, this is a chemistry one. If N is 1.5 moles, how do I find the number of atoms? I need to multiply this by Avogadro's number. So 1.5 times Na, what will that be, please?
1.5. That's 9.03 times 10 to the 23.
Okay, that was kind of like part A, part B. Now this was part A here. Now part C. Yeah.
Hugo, are there the answers?
No, I'm just putting the videos up. But if you have the past exams, they're in from past exam questions. You could find the answers.
You did too?
I thought I made it. All right, I'll make it available again.
Oh yeah.
Yeah. Good. Okay. If the molar mass is okay, so now, sorry, do you need to write that down? Now, part C. I tell you that the molar mass is 4 times 10 to the minus 3 kilograms. So that's the mass for 1 mole. What's the mass for 1 atom? So what do I do?
Divide by Avogadro's number.
Good old Avogadro. So dividing this by Avogadro's number will change this from a mole to an atom. So how much is that now, Avenue?
6.64 times 10 to the minus 27.
Okay. Right, now, last part of this question. The gas is now released from the cylinder until the pressure falls to 5 times 10 to the 5, and the temperature and the volume stays the same. How many moles are remaining in the cylinder? Okay. Can I scroll down?
Is that the answer?
That's the answer for that part, yeah. It's the mass for 1 atom. Now, let me just redraw what you had, okay? At the beginning, what did I tell you the volume was? 2 times 10 to the minus 3. What did it end? Was 1.5, and the temperature was 300. And I asked you for the pressure. What was the pressure?
1.869.
What was it, Brendan? Sorry,
1.869,750.
Okay. Then some of the gas is released, but the volume still stays the same. Will the moles be the same or different? It will be different. We're told the temperature stays the same, and we're told now that the pressure is 5 times 10 to the 5. And we would like to know the moles. So again, just using ideal gas law. So I get PV over RT. So can you please do P multiply V divided by R multiply T?
Um, 400.9 times 10 to the 3.
No, it has to be smaller than the number it was previously, which is 1.5. It's a constant, Ali, 8.31. You know this from chemistry too.
401123.
Maybe, let me just check that I typed the question right, so. Did I say the volume was 2 times 10 to the minus 3?
Yeah.
Yeah.
To the 3,
You
not
said
minus.
that the volume was constant.
You said that the volume
Yeah.
is 2 times 10 to the 3.
To the 3?
Mm.
Ah, rats. That's the problem.
So it should be minus
Yeah, take that. Guys, I'm sorry. The volume here, did I say 3 or minus 3?
Well, initially you said -3.
Oh yeah, minus 3.
But then down.
Sorry, that's still a minus there.
And was right.
Yeah, sorry, that should be minus 3. Okay, now try it again.
0.4.
Beautiful, 0.4. Great, okay. So, how many moles are in the cylinder? 0.4. And the very last part is, what's the mass of the gas that's been released? So how many moles left? 1.5 minus 0.4 equals... Yeah, that's 0.9 moles have left the gas. So we just do 0.9 times the molar mass, like you said, which was given as 4 times 10 to the minus 3.
3.6 times 10 to the minus 3.
Yeah, what happens here is 0.9 moles left the tank, and they want to know what's the mass of this. So I multiply by that number, which is the molar mass it's given, yeah. Now look, these material questions, they don't come up in every exam, but I'm telling you, if you get an exam question that has the ideal gas law in it,
Do it.
definitely do it, okay? Because you do it in chemistry as well. Right, so on to the second one now. Can I close this?
1.5 minus 0.4.
Yep, that's how many moles left.